Sushruta for NEET is now available on the Google Play Store. Try it out for free.
So we continue our discussion today with um, with a quick look at light. Okay. So today this is easy material. That's why you should do very well with this material. Okay, and you should learn this material in such a way that you maximize your your chances of doing well. Um, what when you study light, you know it's very very important to understand the basics. Well, it's actually very simple. So and this is just pure geometry. You must understand the geometry associated with light, and if you understand geometry and you listen to your teachers in class 8 and 9 and 10, this will be very easy. Okay, so let's start with this law of reflection. Incident angle is equal to the reflected angle. Now it is very important to understand reflection and refraction, right? Now, reflection happens when there is a mirror. That everyone understands. Okay? But reflection also happens when there is a transparent layer like glass. Okay? I'm sure you've seen it, like, or water, right? I'm sure you've all seen it. Okay? When you stand next to, like, say, a lake, right? And you look at it, it's a clear lake. You will not only see the trees, but you will also see all the way to the bottom of the lake. Okay. Now, when you see the trees, there is reflection. When you see to the fish and the um, the trees below or the plants below, that is refraction. Okay, very simple idea. Now, in reflection, whether it is the water or it is the mirror, in mirror there is only reflection. Okay, why is that? It is because there is a layer in the mirror that completely reflects everything. Okay, now a mirror typically is covered by a piece of glass, right? Now that glass will undergo some refraction. Okay, so you must remember that. Now, um, basically, in a mirror there is a reflecting surface, right? So reflection occurs when there is a reflecting surface. Okay, now there is a case for reflection when there is also refraction. Okay, that is, we will come to it later, but now let us look at the case of the where there's a mirror, mercury, right? You have mercury, you have incident angle equals reflected angle, right? Incident angle, like, let's say there is a lady looking at a mirror, right? Now she holds up a mirror, you see all these people, right? We are not talking of the people with doing the selfies, right? We're talking about people with an actual mirror, right? She's doing her putting on her tika, etc., right? So when that happens, the mirror will be like this, right? And if they go to the side, they will see that side, right? So from that side there is a incident angle to the mirror. Okay, now, so, and there are a lot of light. The world is full of light, right? So all these light rays hit the incident rays, a lot of incident rays from the outside that hit the mirror and get reflected into this side, the reflection side. What we see with our eyes are very sensitive. They capture Among all the rays that hit the mirror, they capture a very small and finite portion, and these rays. Okay, so a set of rays that hit the mirror and reflect off of it and hit our eyeball. Those rays are captured by our eyes, then go to our brain, and then we see an image, right? So that's how this works. So now if you have a spherical mirror, right, also the same thing happens. Okay, you have a an incident ray, and then it is reflected. Okay, a spherical mirror, you can think of a spherical mirror as a series of mirrors. Okay, every one of them, if you draw a line here, incident ray equals reflected ray. Okay, now what is the line that you draw? You draw this, the line that is perpendicular at that point to the mirror. So if you have a spherical mirror like that, you draw a line perpendicular, right? Then incident ray equals reflected ray at that point. Okay, so as a result, so if you have MP and C is the what is called the center of curvature, right? So the center of curvature, so think of the mirror as a circle, right, or as a arc of a circle, right? At every point, right, at this center of curvature is the center of that arc of that circle. So you have a full circle, this is the center, right? So now at every point, the angle made at the, so if you have a ray like this that hits here, right, you draw a tangent at P, right? Draw tangent at P, and then therefore MPC, right? Let us call the tangent as TT prime. Okay, so MPC will equal CPM. Okay, incident angle equals reflected angle. Okay, so now what essentially happens is that all these rays which hit the mirror at using parallel lines will pass through F. That's the most surprising thing of this, right? You have a ray here, it will make a smaller angle, but all those rays will pass through F, and they will form an image which is a perfect copy of this, only it will be smaller now. When you had the flat mirror, the size of the image, the incident and the reflected will be equal. Now, if you have what is called a concave mirror, it will be smaller if the image is behind the focus or behind the center of curvature. Okay, behind the focus. Okay. This distance from F to the mirror is called the focal length. Okay, this point F is called the center of focus, and its distance from the mirror, using the line that connects the center of curvature and the and the focus, this line will give you the total length. Okay. Now, typically the radius of the of the curvature of the mirror, right? The radius divided by 2 will give you the focal length. This length will equal that length. Okay, so now you therefore have the length F equals half the radius of curvature. Radius focal length is half. So that's how you solve these problems. Draw a tangent, right? And then you find that you think of it as a flat mirror at each point where you draw the tangent. Therefore, incident angle equals reflected angle at that point, and the perpendicular will go through the center, right? This circle geometry. So it's very straightforward geometry. Draw a tangent, perpendicular tangent, you draw what is called a normal. What is perpendicular to tangent is the normal, right? Incident angle equals reflected angle at each of those points. Okay, so as a result, you will have a real image in the case of a concave mirror, and in the case of a convex mirror, you will have a virtual image. Okay, So remember that. And the virtual image typically will be bigger when you're closer. Okay. That you may see, right? When you the convex mirror, right? Where do you see the convex mirror the most? I'm sure you all seen the flat mirror in your home, right? The convex mirror is always there in the side of each car. Okay. The left side, the right side, you will always see the convex mirror. Why do they have the convex mirror there, right? They have the convex mirror because they want you to be able to see far off images in your uh, frame of view, right? You are sitting inside the car, you want to see far off images behind you, right? So for that, they have this kind of a mirror. This kind of a mirror is a mirror shaped like this. There is light coming here, and then it forms an image behind, and it is typically a virtual image. Okay. Now, what happens in a convex mirror is when it's at a distance, it will appear much smaller, and as it comes closer, it will appear larger at a distance, and when it comes closer, it will become really big. Okay, so that's the convex mirror. Okay, now the pole is the geometric center. So if you have a mirror like this, the you have a arc, the center of the arc, point P there is called the pole, right? And the line drawn through the pole, which hits the center of curvature, is called the principal axis. Okay, ray incident, well, incident angle will equal reflected angle when it comes from anywhere, hits that point. Okay, so think of a a uh, convex or a concave mirror as similar to a flat mirror. It's very similar to a flat mirror, only the it is think of it as many different flat mirrors. Okay, series of flat mirrors, each of which is a is tangential. So when you have a ray, think of a flat mirror at that point, which is tangential. Okay, and therefore that's how that works. So reflection of rays parallel to the principal axis. So any ray that is parallel to the principal axis will go through the focus, through the principal focus. Principal focus is half the distance from the center of curvature. You can easily understand this. Okay, so you draw a parallel line, draw this angle will equal this angle, right? Therefore, what will be this length versus this length will equal half that length, and it will be true for every parallel ray. Okay, so all parallel rays will come and hit your center of focus. Okay, and now the most important, so the word paraxial approximation, right, made from para, which means close, axial means axis, hence paraxial means lines close to the axis. Incident rays make a small angle with the principal axis, hence we can approximate for sine theta equals theta. Only rays close to the axis passes in optical system, hence an optical deals with paraxial rays. Okay, most optical systems deal with rays that are close to the axis. Incident rays which make a small angle with the principal axis. Okay, now how do you measure the focal length? Right? So tan theta here, tan theta is what? Tan theta I equals md by cd. Okay, see, this angle is I, this angle is also I. So tan theta equals md by cd. Now, you also know that this angle, theta I plus theta r equals See, this line and this line are parallel. So therefore, 2 theta I equals this angle, right? Vertically opposite angles, right? So now tan 2 theta I equals md by qd. Okay. And now you can, when theta is small, you can say that tan theta I equals theta I. Therefore, you end up with theta I equals theta R equals md by qp. And you already know that md by dc is equal to theta I, right? And 2 theta I is md by qd. Therefore, you can say that md or dq equals half of dc. Okay, it comes from the paraxial approximation. Okay, so this is how this is derived. And why do we teach you this? This is an important derivation which typically you don't learn, but it is worth learning. It comes from the paraxial approximation, okay, which says that for small angles, right, sine theta equals theta, tan theta equals theta. Therefore, you just do this. One becomes tan 2 theta, the other becomes tan theta. Okay, so paraxial approximation is necessary to determine this incident angle and reflected angle. So remember the important rule: 1 by v plus 1 by u equals 1 by f. So which is v, which is u, which is f, right? Typically, u is the distance from the real object to the mirror. V is the distance from the image to the mirror. F is the focal length. What is the focal length? The focal length is QD. Okay. So 1 by V plus 1 by U equals 1 by F. So focal plane. Okay. So where is the ray optics is very simple and it is similar, right? And V over U is, what is V over U? V over U is also called the, is also the magnification. Size of the image versus the size of the uh, um, object is magnification. It is also the ratio of the distance from the object to the lens, object to the mirror, and from the object to the to the image. Object to the image is V. Okay, so V by U is also the magnification. What is the magnification? How big it actually is, how big it appears to how big it actually is. Remember that things that in a circular surface, right, or in a circular concave mirror, there are real images, and the closer you are, the better. Okay, now when you have virtual images, you must, instead of using a negative, instead of using a v, you must use a negative v. So 1 by v plus 1 by u equals 1 by f, but in some cases the v becomes a minus v. Okay, so to keep that in mind. Okay, so I'm so 1 by v plus 1 by u equals 1 by f, v by u equals magnification, and you have your ray optics. Between these three, and you have v by between these three, you can do most of the problems in dealing with mirrors. Now, dealing with refraction, you have sin I by sin r equals refractive index. Okay, but when you have multiple forms of refraction, things get complicated. Okay, now when you go from a rarer to a denser medium, it comes like this and it will go down, right? So uh, sin I will be greater than R when you go from air to glass or air to water. Air is the rarest. Water is denser. Glass is densest of the three. Okay, but then you can change the refractive index of all these types of glass. Certain types of glass will have less refractive index, certain types of glass will have more refractive index, but the typical values range between 1.4 and 1.6 maybe. Mostly 1.4. We have kind of say, okay, 1.5, So, but it's not a given. Okay, sin I by sin R according to Snell is N2 by N1. N2 is the N2 is this, sine I, sine R. Okay, sine I by sine R equals N2 by N1. N2 is the refractive index of this medium. N1 is the refractive of this medium. N21 is when you go from this medium to this medium, which is N2 by N1. Okay, so you have a very clean answer there. Okay, sine I by sine R is N21, sine R is less than sine I, and R is less than I. Refracted ray bends towards the normal. Okay, now when you go from denser to rarer, right, R is greater than R. That you already know, right? And but then in either case, sine I by sine R equals N2 by N1 or N21. Remember that. Okay, now when you have multiple refractions, right, you find that the incident ray travels parallelly. You have the air to this one, theta. Theta 3 equals theta 1. Theta 1, theta or theta 2, theta 2, right? So sine I by sine R equals N2 1. In the second case, sine I by sine R equals N1 2, right? So N1 2 equals 1 by N2 1. So because of that, it arrives like this, uh, comes down parallel. So these two lines are parallel. You see, this line and this line will be parallel. You see, it's only like displaced by a short distance L, which is called the lateral shift. T is the thickness of the glass and L is the lateral shift. Okay, so T is the thickness of the glass and L is the lateral shift. Okay, so if you have multiple layers, then it will refract, and but then at the other side you will have theta 1 equals theta 6. Now, if you look at fiber optics, they use this. They have two types of fiber optics. What is called step index fiber, and then they also have graded index fiber. A graded index fiber, this is what will happen. There will be a lot of refractions, and then there will be a movement of the light at parallel theta 1 equals theta 6. Okay, so laws of refraction, sine I by sine R equals N2 by N1. Okay, so there you have it. Okay, so the effects of refraction, you have this idea of the apparent depth, distance from the surface where the refracted rays appear to meet. The real depth, the depth from the surface where the refracted rays actually meet. Okay, so the apparent depth versus the actual depth, d prime over d, right? So this happens when you have when you have a, let's say, a bottom which is reflecting, right? That you have so many of these ever silver vessels, right? When you have an ever silver vessel, you will have this idea of the apparent depth, right? So d prime over d, right? So now how do you calculate that? You calculate that using apparent depth, or by the actual depth will be the refractive index of the medium, and you can do this derivation yourself, right? So remember, always the most important idea is that is the paraxial approximation. What is the paraxial approximation? Sine theta equals theta. Okay, so they ask you what is the paraxial approximation. Typically, it means something dealing with sine theta equals theta. The incident angle equals the refracted angle. Always true. But when you do an approximation, you see that the small angles sine theta equals theta. So that is the fundamental idea that you must remember. Sine I by sine R, N2 by N1, refractive index. And then we also use finally this when you look at apparent depth by actual, what is that? Actual depth by apparent depth, that will be, it will appear closer. When you have look into water, it will appear closer, right? So you must have seen that, right? So the apparent depth is less than the actual depth. So d prime by d over d prime will equal the refractive index. D over d prime will equal the refractive index. Keep these ideas in mind. So finally, we will look at the sun, right? Due to refraction of rays from the sun by the Earth's atmosphere, the sun seems to appear above the horizon before it actually rises. Okay, so what does this mean? the inclination of the setting sun. It means that, when you see the sunset, right? What happens, or when you see the sunrise, I don't know if you have seen this Mahabharata, right? In Mahabharata, Arjuna and Karna were fighting. Okay? And then suddenly what happens is, when the sun sets, they are supposed to stop fighting. They don't fight after the setting of the sun. So what happens is, they Arjuna was losing. Okay. So then suddenly Krishna uses his hand and then he does this before the sun sets. Right? That's not what's happening here. Here, what is happening is that the that the person is seeing the sun as though it is here. Okay? To him, the sun is at S prime, but actually it has already set. Okay, the sun appears to be above the horizon. In this, it is actually like the sun is here, but it appears to be here. It feels that it has already risen, right? But in Krishna's case, it was the setting sun. It had already set, but it appears, right? It was the other way. Right? So this is what will normally happen, right? It will appear to be there, but in Krishna's case, he made it disappear. Okay? The setting time, the rising time, it goes like this, right? It goes like this. So although the sun has not yet risen, when do you say the sun has risen? When, if you had parallel rays, you looked and you draw a tangent from your eyesight, you will see it, right? But then if it is there, you won't see it. Why is that? Because you are so small compared to the um you are only 6 feet compared to the viratness of the earth, right? Earth is so big, right? So you are just a small person there, right? So you can only see when it's tangential. And what is tangential is called the horizon. Draw a tangent from this point out, that is the horizon. Okay? Now, the sun has not yet crossed that horizon. It is there, but actually you think it is there because there is a refraction of the rays. Okay? So this is very, very simple ideas, but you must learn refraction optics and reflection optics very well. And we aim to teach it well enough, but you still have to do a lot of problems. Only then you will get these questions right. Okay? So this is refraction. Now we are going to go to ray optics. Okay? Ray optics discusses diopters and everything, right? So I already discussed 1 by u plus 1 by v equals 1 by m. So before we go to ray optics, let me look at a little more refraction, right? When you do refraction, right, you note the conventions. Okay, spherical surfaces, they have convention. Okay, now refraction by mirror and lens. Okay, when you do mirror and lens, uh, note the convention, right? So here he is saying that n1, n2, right? N1 is um, uh, thinner, n2 is denser, right? So it's like air to glass, right? So when he does that, right, and it's a curved surface, you say minus u plus v. Okay, but when it shows up here, you say minus u minus v, etc. Okay, so note this convention. This is for single refraction. Okay, remember, in a lens you have this other form, and this is the most important idea. N2 by v minus n1 by u equals n2 minus n1 by r for a single refraction. Okay, now n2 by sin I by sin r equals n2 by n1, right? But remember this formula, n2 by v minus n1 by u equals n2 minus n1 by r. Okay, so now when you apply it twice, you'll end up with this 1 by u plus 1 by v equals 1 by n, right? So assume small aperture and the paraxial approximation is valid. Therefore, n is closer to p. So here what they are saying is sine at this point alpha, beta, gamma, I, and R, they are all small angles. Every angle is a small angle, although they make it big, right? They're actually talking about very small angles. So at small angles, tan theta equals sine theta equals theta. Okay, that's called the paraxial approximation. So you must remember this formula: n2 by v minus n1 by u equals n2 minus n1 by r. V is the distance of the image from the lens. U is the distance of the image from is distance of the object from the lens, right? And n2 is this side, n1 is this side. Okay. So you must always know when what kind of image gets formed. Okay. You can get virtual images both with concave and convex surfaces. But remember this one, okay? And here he is deriving this formula: n2 by v minus n1 by u equals n2 minus n1 by r. You can take a quick look at this and you can try to derive it, or you can look into your textbook. I'm sure they've derived it there. Okay, but this is very well worth learning. I will not be going into the details of this today. Okay, but it is very important to learn this derivation because it will teach you how you can apply geometry in the context of Snell's law. This is particularly for students who are going to be taking the JEE. Okay, students who will be taking the JEE, you must make it a point to understand this derivation. Okay, the angle I equals alpha plus beta. The angle R, why is that? Exterior angle is sum of interior opposite angles, right? So in that triangle, right? So the angle R is equal to beta minus gamma, right? Beta minus gamma equals R, right? So using these two, he then derives this equation n1, this whole thing, and this whole thing becomes n2 by v minus n1 by u equals n2 minus n1 by r. So please understand how this arrives, and then when you have lenses, you therefore this one only becomes 1 by v plus 1 by u equals 1 by f. But this is the formula that you must know when you have only one spherical surface and you have this Snell's law to be applied. Okay, so remember that and let's move on. Okay, so when you have successive reflections using relative, right, you say this is of a same curvature as that. You can't have this one curvature, that different curvature, right? But that also they do. Okay, and you have different types of astigmatism, right? So this one is called the lens maker's formula. N1 equals 1, N2 equals N, right? So one side is air, okay? And you introduce this lens maker's formula. See, this formula is true if you go from water to N2 and N1. This formula is true when you go from water to glass, okay? When you have successive reflections, you then have 1 by V minus 1 by U equals 1 by F, right? Then you also have the lens maker's formula. 1 by F equals N minus 1 times 1 by R1 minus 1 by R2. What is R1 and R2? R1 is the radius of curvature of the left side, and R2 is the radius of curvature of the right side. So lens makers 1 by F equals 1 N minus 1 times 1 by R1 minus 1 by R2, 1 by V minus 1 by U equals 1 by F. Then N2 equals N and N1 equals 1. Lens makers formula. Okay, so note this is derived from this. So 1, 1, 2, 3, 4. Okay, so they reapply when you have different radiuses of curvature, they reapply it. So note all these formulas. And for converging lengths, symmetric biconvex lens 1 by X equals 2 by R times N minus 1 Now, if n is 1.5, 1.5 minus 1, is 0.5, that is 1 by 2. So the 2's will kind of factor in there. Okay. So f equals r by 2. Okay. So typically that is the equation, right? Focal length equals half the, that's what they do. Okay. So okay. So with that, I'm going to stop for today. Okay, and we will continue our discussion next time. I will continue this discussion, but then I will also introduce your ray optics, and then I will go to combination of lenses, which is what you see in a telescope. Okay, so but remember, 1 by v plus 1 by u, you attempt some problems. Okay, we will then also look at some problems, combination of lenses problems as well. Okay, this length, then I put another length, then I separate the distances, etc. Right? So all those I will do next time. 1 by v plus 1 by u, 1 by v minus 1 by u equals 1 by f. Then we will look at various types of lens problems. Okay, so and we will then look at all these questions in that context, and then we will what I do advise you though in the meanwhile is that you spend some time looking at your textbook. I always advise students to study from H.C. Verma. Okay? H.C. Verma discusses optics, I think, in the first book. Okay, H.C. Verma, right, discusses optics, or maybe in the second book. Okay, so you look at um, geometrical optics, the first book, chapter 18 in H.C. Verma. So what I typically suggest students do is you buy H.C. Verma. Okay, in whichever, if you're studying in Hindi, buy it in Hindi. Okay? If you're studying English, buy it in English. Okay, what you should do is you should look at the solved problems in H.C. Verma. Okay, so that is how I typically teach students. Okay, look, you study the chapter, then look at the solved problems. Very important, look at the solved problems in H.C. Verma. That will teach you so much. That will teach you the material very well. Then when you don't understand, you listen to the lecture. Okay, so this is typically how you one way to do it. The other way is to first just listen to 3 lectures in IIT PAL. 3-4 lectures. Once you listen to the 3-4 lectures you have, and then look at these slides. The thing you should not do is just scan through the slide, and then go to the problem solver. There must be one step where you look at read the HC chapter. Why do we teach this? The way we teach it, it is to facilitate your better understanding. Okay, we want you to be able to make use of our app along with the material that we do teach. Okay, so that is very, very critical to the success in this program. So learn the material well, and part of that is first understanding it cursorily once, going into the depth. Particularly if you're taking JE, right? Taking JE, all the JE students must know things better, because the problems they ask are aimed at tricking you. And so they are very proud of the questions they set. You should be very proud of solving them. That is very important. That's why we very sensible. Okay. So with that, I'm going to stop presenting, and then I will see you all next class. But next class, I'm pretty much going to get started again with class, or in 2 classes, we are going to get started again with class 11, because we want to be able to get students to the fresh batch to start, and we start typically with calculus. Okay, calculus and vectors. Quickly go over that so that you learn all the material when you're class 11, and then we take things forward.